unlocking the secrets of optical vortex generation, a game-changer in photonics. In recent years, the fascinating world of optical vortex beams has captured the attention of researchers and technologists alike. These beams, distinguished by their orbital angular momentum, OAM, have opened up a plethora of applications ranging from optical micromanipulation to advanced imaging techniques. But what exactly makes these beams so special, and how can we generate them more efficiently? Let's dive into the intriguing realm of spin-orbit coupling in van der Waals materials and discover how it can revolutionize optical vortex generation. Introduction. Optical vortex beams are not just a scientific curiosity. They are pivotal in various fields, including optical micromanipulation, chirality sensing, and phase contrast microscopy. The unique property of these beams lies in their topological charges, which are defined by the number of 2π phase shifts along the beam's axis. This characteristic not only enhances the degree of freedom in optical systems but also significantly boosts data capacity for communication. Moreover, these beams can be utilized to multiplex qubit states, paving the way for exciting advancements in quantum optics. Since the introduction of optical vortices in 1989, extensive research has focused on developing methods to create light sources that exhibit OAM. Over the years, several commercially available solutions have emerged, including spiral phase plates, Q plates, and computer-generated holograms, also known as spatial light modulators. While these methods have proven effective in generating vortex beams, they often require bulky optical setups, leading to a growing interest in more compact and integrated photonic solutions. Early attempts at creating compact vortex generators involved liquid crystals, which offered some level of integration. However, recent innovations have introduced techniques such as fork gratings, metasurfaces, integrated microcombs, and inverse design devices, all capable of generating optical vortices on a chip. Despite these advancements, existing on-chip solutions often rely on nanoscale features that necessitate expensive and time-consuming nanofabrication processes, which can hinder their practical application due to challenges in achieving adequate signal-to-noise ratios. The controversial shift, spin-orbit coupling. Traditionally, methods for generating optical vortices have focused on manipulating the phase front of light to convert unstructured light into helically structured light. However, a groundbreaking approach has emerged that utilizes optical spin-orbit coupling to create optical vortices. This concept, theoretically validated in previous studies, suggests that when a circularly polarized light, CPL beam, interacts with a uniaxial medium, it can generate light with opposite-handedness, thereby imparting OAM to the transmitted beam. Recent experimental validations using materials like lithium niobate and beta-barium borate have demonstrated this phenomenon. However, these materials exhibit limited birefringence, necessitating the use of thick crystals to achieve sufficient conversion efficiencies. This limitation has prompted researchers to explore alternative materials that can facilitate more efficient vortex generation. A new era with van der Waals materials. In this study, we propose a novel optical vortex generator that leverages the unique properties of van der Waals (VDW) materials, specifically hexagonal boron nitrate (HBN) and molybdenum disulfide (MOS2). These materials exhibit significant birefringence, allowing for efficient spin-orbit coupling and the generation of optical vortex beams without the need for complex fabrication processes. For our experiments, we utilized an 8 micrometer thick HBN crystal slab to demonstrate the generation of optical vortex beams. The topological charge of the vortex was confirmed through an interferometer setup and numerical simulations. We achieved a conversion efficiency of 0.30 with the HBN crystal when illuminated by a 594 nanometer laser. Additionally, using a 26 micrometer thick MOS2 crystal, we recorded a conversion efficiency of 0.46, approaching the theoretical maximum of 0.5. Remarkably, we also observed spin-orbit coupling in a 320 nanometer thick MOS2 flake, achieving a conversion efficiency of 0.09. Our simulations suggest that employing a Bessel beam could further reduce the generator's thickness and potentially achieve near-unity conversion efficiency. Results and implications. The experimental setup for generating and characterizing the vortex beam involved a straightforward configuration that included a single-mode fiber, lenses, and polarizers. By focusing a circularly polarized beam through the HBN crystal, we successfully generated an annular intensity profile indicative of the optical vortex. The topological charge was verified through interference patterns, revealing two-armed spirals that confirmed the expected OAM values. The implications of this research are profound. By utilizing VDW materials for optical vortex generation, we can create compact, fabrication-free devices that are suitable for both small and large-scale applications. This advancement not only simplifies the generation of optical vortices, but also enhances their accessibility for various technological applications. Chapter Conclusion. In summary, our exploration into the realm of optical vortex generation through spin-orbit coupling in van der Waals materials has unveiled a promising pathway for creating efficient and compact vortex generators. The successful demonstration using HBN and MOS2 crystals highlights the potential of these materials in integrated photonics, paving the way for future innovations in optical technologies. As we continue to refine these techniques, the possibilities for applications in quantum optics, communication, and beyond are boundless. Chapter Conclusion. Join the discussion. What are your thoughts on the implications of using van der Waals materials for optical vortex generation? Do you believe this approach could lead to significant advancements in photonics? Share your opinions in the comments below.